Today we are gonna go with that module computer software basics, and today we are gonna learn data encoding. Learn how computer encodes character as from ASCII to Unicode UTF. Introduction. In the previous room, you learned how numbers are represented in the computer as binary digits bits, and how these bits can be grouped into hexadecimal digits. We also explored how to express colors using numbers. Now, if everything is stored as number, how do we convert them to letters, punctuation, and emojis? In this room, you will learn that characters are just numbers with the agreed meaning. That agreement is called an encoding. Have you ever opened a document, visited web, visited a web page, or downloaded movie subtitle files only to see the file appear as weird gibberish? One reason for that is the user who saved the file and user who opened it are using different encoding. Representation is the idea that data lives as bit and numbers in memory. At the same time, encoding is a specific agreed upon mapping between numbers and meaning, such as which number corresponds to the character A in text. Each character each character like Q5 or what is that apostrophe mark, something like that, is assigned a numeric code. So a string becomes a consequence of numbers that the computer stores and moves around just like any other data. Learning objective. Upon completion of this room, you will learn about ASCII, Unicode, UTF-8, UTF-16, UTF-32, how emojis is encoded, and how what causes weird gibberish character. Prerequisite is, let's see, data representation. We learned this in the previous room, right? Yes, we learned this. This video will be uploaded soon, I guess. Let's go. ASCII. We already learned that the digital computers only understand zeros and ones. Starting from 0 and 1, how can we save and display text? For example, how can we save the text TryHackMe in a file? What will such a file contain? To be able to answer this, we need to agree on what bit represents T, what bit represents R, what bit represents Y. Oh, this is TryHackMe, and so on. Let's say that we all agree to represent T with the following stream of bits 0 1 0 1 0 1 1 1 0 0. Then all computer systems should store T the same way, and the letter when computer encounters it will recognize it as T. Of course, we need to do this for all letters in the alphabet, digits, and special characters. This approach requires a standard that the computer manufacturer designer and the programmer agrees to adhere to. One of the earliest standard of English letter was ASCII. ASCII stands for American Standard Code for Information Interchange, and it is an early character encoding from 1963 that uses numbers 0 to 127 to represent English letters, digits, punctuation, and some control characters. Remember that A stands for American, as this will come in handy later. As you might have noticed, the original ASCII was limited to 7 bits. ASCII acts as a small polygonal dictionary between text and numeric code. Consider the following samples. From the original ASCII table, since the table has 180 entries, we only made a brief section to give you an idea of how things are represented in ASCII. Decimal, hexadecimal, binary, symbol, and description. 48, decimal is 48, hexadecimal is 30, binary is this number, symbol is 0, and description is 0. Same goes for year. Uppercase X, 88, 58. Oh my god. There are several things you can observe. First, the letters are in order. You know the the hexadecimal or decimal number for B. You can figure out the decimal number of A and C and the lowercase letter. For example, A, B, and C are assigned the hexadecimal numbers 61, 62, 63 respectively. Same for the uppercase letter. To A to Z and 0 to 9, when ASCII encoding, a computer system reads 41 in a file and displays A on a screen. When it reads 42, what the hell? A computer. Wait a sec. Uh, there is. Wait a second. Let me read it here. What it reads 42, it displays B and so on. Secondly, each character has its own ASCII. For example, wait a sec. Let's go from start. There are several things that you can observe. First, letters are in order. If you know the hexadecimal or decimal number for B, you can figure out the decimal number of A and C and the lowercase letter. For example, A, B, and C are assigned the hexadecimal number 61, 62, and 63 respectively. Same for the lower uppercase letters A to Z and 0 to 9. When asked using ASCII encoding, computer system reads 41 in a file and displays A on screen. When it reads 42 and it displays B and so on. Secondly, each character has its own ASCII. For example, a bracket is represented by the hexadecimal number 5B. Wait a sec. What's up, app setting? How the hell am I supposed to off that? It seems cool. Uh, Sorry about that. Let's see, the timer is 20 minutes. All right. Already 20 minutes after recording. 9 minutes. TryHackMe in ASCII. Let's say you open a text file. Why write TryHackMe and save it as text file.txt? How will the file look on the bit level? Let's find out. If you're interested in seeing the storage on disk bit by bit and assuming that it is using ASCII, you will see something similar to the following. Obviously, this is not readable by any human being. These are extract binary represent of all the letters in TryHackMe, followed by a new line. When you open this file, your editor will read these bits and display the following character. And last n is a new line that you get when you enter the key. Because reading binary numbers is cumbers what is this cumbersome. I don't know what the hell is that. And error prone to us. We prefer to use hexadecimal digit as you remember from the previous room. We go 4 bits into a single hexadecimal digit. Our file looks like this in the hexadecimal. And if you want to look up the decimal representation, it would be as follows. However, it is common to use decimal digits. It is more common to use hexadecimal digit when we want to show the bits. Uncommon to use decimal bits, alright. You can use the attached static site yourself to experiment more. European language. ASCII provided a way to encode the English alphabet. However, you need an encoding to support other European languages such as Spanish, German, Polish, Czech, and Romanian. To name a few, ASCII uses 7 bits. To name a few, ASCII uses 7 bits, and with an 8th bit, we get 128 more characters to cover. However, the reality is more challenging. The additional 28 letters are not enough to cover all the letters of European language. The IEC 8859 series international standard created several standards. Each standard covered a set of language. ISO 8859 Latin 1 covered a Western Europe languages like German, French, Spanish, Italian, Portuguese, Catalan, and Nordic languages. Example, Irelandic. What the hell is that? And Latin 2 supported Central West Eastern European languages like Polish, Czech, Hungarian, Croatian, Romanian, and Slovak. In other words, if your document is saved using this and the later read and displayed as it was saved using ISO 8859-2, non-English letters are likely to be displayed differently. Wow, that was interesting. This is how A used. Let's see. Oh, zero. Zero. We cannot type only one word, all right. ASCII, that is very good, very good, very good. Let's go with that. Uh, what is the ASCII code for decimal for the character? It is 64. What is the character that has ASCII code of 35? Let's see. One is 61, all right. That is a number. A, that is way off. A, is that it? This is not that. It is one. No. What is the character that has a ASCII code of 35? Uh, 30. 35. Let's see. We cannot use that. Wow. Uh, which is easier is let's see, 2, let's see, 3 is 5. 30 might be 5. I don't know. Oh, it is not. So here we can change it. Oh, we can change it. Oh my God, I am just. Oh, we can do that. Wait, wait. It was way off. I don't know. What is the name of the character that has a ASCII code of 7? Uh, well, it is kind of hard. Practice it. Even I don't know more about that. Let's go. Let's continue the room. Uh, we learn that ASCII is a 7-bit standard that defines 28 character covering English letters, digits, and basic punctuation. We also noticed how ASCII with its 7 bits didn't have room for characters such as using 8 bits extended. ASCII tried punching this with a regional variants. ISO 8851, ISO 8859 too. Windows 1252 among many others, but this caused chaos. For example, if the sender writes and save using ISO 591 Latin 1, Latin, we will use Latin. The encoding, the recipient opens encoding, Latin 1 encoding, and the recipient opens and reads the document using Latin 2 encoding. They will see R, and it is clear how opening a document requires us to use the same encoding used when saving it. Otherwise, various characters will not be displayed correctly, or even more confusingly, they might be incorrectly replaced. Unlike English, which has 26 letters and needs 52 characters to cover uppercase and lowercase, Arabic needs more than 250 characters to cover its various literature and diacritics. Moreover, the number escalates rapidly when considering Japanese and Chinese. In Japanese, 2000, 2136 kanji logographical characters are considered daily use character as mandated by Japan's Ministry of Education. In fact, the GIS 028 standard defines 6879 characters in Chinese. Educated native recognize around 8,000 characters. Furthermore, the GB 18030 2022 defines more than 88,000 87,088 87,8807. I don't know if I am reading correctly. I am full. And still, we have not considered encoding emoticons, emoji. Oh my god. In other words, it is essential for both the sender and recipient to use the same encoding. Moreover, we need to encoding that can include all the characters from all the languages. This situation brings us to Unicode. Unicode is a universal character encoding standard. It assigns Unicode points to character from all modern and historical writing systems worldwide. Unicode support a interchange processing and display of text in diverse language. In other words, we don't need to worry about picking a specific encoding standard that is compatible with the language we are using. Furthermore, this makes it easy to use different language in a single file or a message. And most importantly, because this is a standard that fits all, we don't need to worry about encoding used by the original author, as they also be using Unicode. Unicode is a character set standard that assigns a unique number to every character across all languages. Example, U plus 001 Latin A, U plus 03A9 Greek, 0 plus 03042 Japanese Hiragana. Unicode 7.0 is currently the latest version of the Unicode standard. It defines the close to 157,000 characters, almost 4,000 of them are emoji sequence. Wow, beautiful. UTF-8, UTF-16 and UTF-32. Uh, because you will encounter UTF, UTF-16, UTF-32, we will briefly cover them without going to too much depth. What you need to know is that UTF-8 is very common on the modern web. It encodes Unicode points into 1 to 4 bytes dynamically. In other words, it decides on the number of bytes based on the character complexity. ASCII character U plus 00000 to U plus 007F use exactly 1 byte, ident- identical to the original ASCII, assuring seamless backward compatibility. Non-ASCII cas- non-ASCII characters like, what the hell is that? U plus 03A9 use 2 bytes, while complex scripts or emojis like fire requires 4 bytes. This flexibility allows us to cover the Unicode standards without wasting bytes. UTF-16 takes a different path. It uses either 2 or 4 bytes per character. Common characters like most Latin, Cyrillic or Chinese kanji fit in 2 bytes. However, rare ones like emoji or ancient script require a pair. Two 16-bit units totaling 4 bytes. For example, a letter A is encoded as U plus 0041, while the emoji needs 2 and is encoded as U plus D83D plus U plus DD25. Finally, UTF-32 is the simplest but also most wasteful. Most wasteful. Every Unicode point uses exactly 4 bytes. For example, A is encoded as extra zeros and 0 is encoded and they add extra zeros. Let's look at a few more examples. One of the Chinese letters that appear on the offensive Linux distribution, such as Kali, is, which means dragon. In Unicode, it is this or this, depending on whether it is UTF-16 or 32. This smiley face is nothing more than this in UTF-32 for a computer that's likely this one. Uh, This the Japanese letter tsu, which some people use as a smiley face in some region outside Japan. It has a code this one or this one depending on whether it is UTF 16 or 32. Arabic letter ta, and some people use it as a smiley outside the Arab world. It looks close enough to smiley's face from a Unicode perspective. That is this one. And the Unicode, the Black Knight in the chess uses the Unicode this one. In other words, the computer reads and shows the Black Knights thanks to Unicode. We created a static site to help you look characters and explore one available most. This is called. What is the uh what the hell is that emoji? I never saw that. Uh, Let me do this. Copy. Very easy. Very easy method, guys. You can always do this. Uh, this one. Copy. Paste. What is UTF 16 of encoding? What is it? Is stu, right? They said it is something like stu. It is a Japanese character. Stu. What are they asking? Unicode 16. Copy and paste. What the hell? What is the UTF-16 encoding of stu? Note that stu and stu are two different characters. Yeah. We use this. We need this. Sorry about that. See. Always read the question, guys. Always read the question properly. Let's see. What is the character that has a following UTF-32 encoding? Let's see. Wow, that is a emoji. What is the character that has a following? Oh, this one. Let's see. Control C. It's a knight. Let's go, guys. Let's go. In this room, we learned about ASCII and its limitation, and about unique and three encoding standards: UTF-8, UTF-16, UTF-32. We explored how Unicode enables to use cover not only the world's language but also symbols such as chess pieces and emojis. If you are curious to see how computers manipulate data, join the Python demo too. We are adding toward that. Let's go.